goes.
Well, it's my pleasure.
Thank you for your patience in helping us work through these as well.
Oh, you're welcome.
3 months from now, we'll have this down. It'll be an easy process.
Okay.
Hey, Rodney, it's good.
Webinar today, Hunter Nolan is going to talk about fracking and water quality. First note is everybody connected is muted initially, so if you want to ask a question or make a comment, you have the ability in the dashboard that's on your screen to unmute yourself. If you have problems with that, there's at the very bottom of the left-hand side, there's it's up at the top, it's a little panel on the left-hand side. At the bottom of it, there's a way to raise your hand. So if you raise your hand, then we can unmute you as well. But if you do want to make a comment, make sure that your microphones are not muted before that you make the comment. Sam Fowler is the Auburn faculty member that is working in fracking and water quality area. He had a conflict today, so he's asked Mr. Hunter Nolan to sit in for him and speak today. Hunter's an expert and very knowledgeable on the subject. Auburn is involved in a lot of other water quality related research that's not associated with fracking. So the civil environmental engineering have a number of projects going on. If there's anyone that has interest in water quality outside of this specific subject related to fracking, if you'll send me an email and let me know, then we'll either try to set up a separate webinar or we'll get those topics on in a later monthly webinar. Our next two webinars have already been established as far as the agenda goes. On June the 12th, Dr. Virginia Davis and other faculty members will be talking about nanotechnology, bio-nano, and polymer research. Then on July the 10th, Dr. Charles Ellis and Dr. Mike Hamilton will be talking about microelectronic packaging and nanotechnology. So both of those sessions will start at 2 o'clock Central Daylight Time. So you put those on your calendars and we'll send out emails and as reminders. We also will have a link to this presentation. It is publicly releasable, so we'll have a link and that'll be set up after the presentation. At this time, I'd like to ask Stan Graves to say a few words. These webinars are being hosted by the Industrial and Research Committee of the OVPR Research Advisory Board, and Stan is the chair for that committee. So Stan. Okay, Stan must be having problems with his microphone, so we'll get Stan on later in the session and get that worked out. I'd like to go ahead and introduce Mr. Hunter Nolan. Mr. Nolan is a registered professional engineer and board-certified environmental engineer. He holds a Master of Science degree in environmental engineering from Montana State and a Bachelor of Science degree in aquatic biology from the University of Texas at Austin. He has 29 years experience in environmental engineering and related scientific instruction activity. Since the expansion of the use of hydraulic fracturing in the unconventional oil and gas area, Mr. Nolan's been involved in a lot of different projects associated with environmental management, site development, water resource planning, water management, logistics, water treatment, disposal. So he's a real expert in this area, and we're glad to have him here today. So, Mr. Nolan, we'll turn it over to you.
Well, thank you very much, and it is a pleasure to speak to you all today. I'd like to start by just giving you a little context as to my viewpoint of this subject and hopefully set the stage for what you can expect to hear. I'm responsible for a business unit in a company called CDM Smith, and we are an environmental an infrastructure engineering company. We've been around since 1947, started up in Cambridge, Massachusetts. We have offices all over the country and all over the world. And we started back in the day when protection of public health was really important, soon after the end of World War II, and with a great deal of focus on water management issues, water treatment, water protection, etc. And as the environmental industry expanded and became more complex, we did along with it. And today we're a firm of about 6,000 staff with offices all over the world. Now, we've worked for the oil and gas industry for a lot of years, but not until recently, say starting in around 2000 and after that, has the complexity of water management become really significant. And it is today, and the reason for that in the oil and gas industry is because of the very rapid expansion of the use of hydraulic fracturing in developing natural gas and oil resources from very low permeability formations that they call unconventional oil and gas development. And so we as a firm have responded to this need for our expertise, and what I'll give you today is just a perspective of what we've learned and maybe some food for thought for you all on this call on where maybe you can bring some value to this development challenge as well. Now, there is apparently a delay between the time that I push the button here on the computer and when the next slide comes up. So hopefully now you see the presentation outline. If it becomes cumbersome and I'm speaking to a slide that you don't yet see, if somebody could let me know, and I'll slow down between slides. So first I'll give a summary of the shale resource and the implications, the economic and global and even some geopolitical implications to what all this means to society. Second, I'll talk, I think, more specifically to what many of you may be interested in, and that is water management and treatment, and what are some of the really important aspects of that in the industry. And then finally, I'll end with some thoughts on what I think are some research needs and opportunities with respect to water in the unconventional oil and gas arena. So what you will look at soon, if you're not seeing it already, is a slide that says world energy consumption. And it's got two graphics in it. The left-hand graphic shows the growth of world energy consumption to about 2035. And as you can see, it's a very steep growth. So the world is very hungry for energy and will continue to be. And the red section of that graph is related to primarily non-developed countries. So you can see that's where most of the energy need is and growth is going to occur. And then the blue section of that is mostly developed countries. On the right-hand side is a representation of where that energy is coming from, the different types of energy, from nuclear to renewables, natural gas, coal, and liquids. And what you can see from this graph is that between now and 2035, there's a need for fossil fuels, natural gas, coal, liquids, to continue to be accessed, developed, and utilized to meet the demands of the world's energy needs. I think we'd all like to see the green curve, the renewables, be much steeper than it is. We have some technological limitations there, and of course some capital limitations in how fast and large scale we can take renewable technologies forward. And frankly, we're going to need some substantial technological advancements to occur in order for that renewable curve to get up there and compete with the fossil fuel curves, and especially to replace those over time. So that ultimately creates a need to continue to generate a great deal of energy using fossil fuels in order to meet the world energy consumption needs. Next is a kind of a cartoon graphic, and what this shows is how traditional or conventional oil and gas development occurs. What happens is that oil and gas is formed in what are called source rocks. And you'll hear petroleum geologists and petroleum engineers, they often call that source rock the kitchen, which is where all of the oil and gas is in essence created, cooked over time due to organic deposition in these materials. And traditionally, we have accessed oil and gas from very high permeable zones, high permeability formations underneath what are called traps. And you can see on this graphic there's a seal over the top of this yellow area, which is a conventional formation. Up until recently, we were limited economically in acquiring oil and gas from those conventional resources because oil relatively readily flows through this high permeable material, and gas does to be captured by a production well. So what is new, and it's new since, well, it was begun to be investigated in the early 90s, but it really wasn't developed in a reliable form until early 2000s, and especially around 2006, is the combination of two technologies coming together to allow us to effectively acquire oil and gas from the source rocks. And those are very low permeable materials, and in most cases, I mean, there are various kinds, but shale is the one that's getting the most attention, and it's a really huge resource. So the technologies that have come together are a combination of horizontal drilling and hydraulic fracturing, and I'll get into that into a little bit of detail. So hopefully you see a graphic now that represents another schematic representation of the land surface and some wells pictorially represented in cross-section that are horizontal wells. They go down through from the surface down to the depths of, in this case, a shale material. And as the well is constructed, there is a bend in the casing, in the bore, and so once the formation is reached, the bore is effectively horizontal. And the importance of that is that a lot of these formations, these shale formations, are fairly thin in depth, but they're very expansive horizontally. So if you were to try to drill a vertical well into one of these formations and even fracture it, you really have very little access to the formation from which to acquire oil and gas. But the horizontal drilling allows a very long reach of drilling to stay within the target formation. And along with that horizontal drilling is a process called hydraulic fracturing. And in essence, high pressure water with some conditioning chemicals along with a proppant, and that's typically a sand material, is pumped down these wells at high pressure and controlled with some very high-tech equipment, controlling pressures and observing the reaction of the formation as the fracturing occurs. And in essence, what happens is that there's fractures are created in the formation. The sand flows into those fractures, and when the pressure is released, the sand particles remain in those fractures, and so they keep those fractures open enough for the oil and gas to migrate to the well. And so in essence, what's happening is there is a very large expansion of the surface area of this formation that is available for oil and gas to be released from. Now, without this technique, you might drill a well into this material and you might show a very brief result of, say, natural gas, but that result would dissipate very quickly because there's just no mechanism for that flow to continue to the well. And that's in essence what the horizontal drilling and hydraulic fracturing enables us to accomplish. So in the upper left-hand side of this slide, you see what a shale outcrop looks like. It's a very, very low permeable material. It does have natural fractures in it. The hydraulic fracturing process actually enhances those fractures. And in the lower left-hand corner, you can see a piece of shale that was placed in a vessel of water, and you can see some bubbles, some gas bubbles coming from that shale. So there's a tremendous amount of oil and gas trapped within this rock, and you can understand why by looking at this picture that if you increase that surface area dramatically, then you are enabling a whole lot more of this flow to occur. And that's in essence the technological advancement that has happened over the last 6 or 8 years, really. Next is a representation of the history of fracturing, and fracturing itself has been used for a long time. In fact, it was first experimented with way back in the late 1800s with explosive fracturing. They used nitroglycerin and other explosive materials, dynamite, etc., to try to open up materials to make them flow better. Research or available information indicates that Halliburton was the first firm to utilize hydraulic fracturing. They did so in the late 1940s in Oklahoma and Kansas. And by 1988, it was very common practice for fracturing to take place in oil and gas development. Again, in 2006, there was a real advancement in the utilization of fracturing combined with horizontal well drilling. That happened in an area near Fort Worth, Texas called the Barnett Shale. And there was a sort of visionary petroleum leader by the name of George Mitchell, who had a small independent company called Mitchell Engineering. He had been working with the Barnett Shale, trying to figure out how to economically collect gas from it. And he, in I think it was 1998, joined forces with Devon Energy, and together they really developed this combination of horizontal wells plus what they call multi-stage fracturing. And in essence, the multi-stage fracturing is a process of isolating portions of that well and fracturing it in small portions. But that combination of technologies really allowed what's taking place today. So today, 2013, almost all oil and gas wells are fractured, hydraulically fractured in one way or another. And there's an awful lot of horizontal drilling taking place. In the United States, we have a tremendous resource of shale. So over this short period of time that I've been talking about, we now have access to a tremendous amount of energy that's available to us economically that was not previously available to us. So we have oil and gas basins in various places around the country. And certain of them are very, very prolific. For example, in Texas, we have 2 formations right now that are probably the most active in the country. One's called the Eagle Ford in South Texas, and the other is the Permian Basin in West Texas. And then, of course, in North Dakota, there's the Bakken resource, which is also very active and very large. And then we have some important assets as well in the eastern U.S. The Appalachian Basin carries a tremendous amount of natural gas, and then there's areas in Michigan and other parts of the country as well. So we are now faced with the accessibility of so much more oil and natural gas than we were previously that the whole picture of oil and gas development, not only in the United States but globally, is changing as a result. And here's an example. In the next slide, what I show is a representation of estimated recoverable natural gas reserves. And I spent a little bit of time talking about natural gas because it's an important aspect of this, but I don't want to diminish the importance of oil and liquids as well, because what has happened is that originally this was applied to acquire natural gas from the Barnett Formation, but it has found to be very, very effective too in oil-containing formations. So there's a tremendous amount of this same work that is recovering not only natural gas, but oil and other natural gas liquids as well. But looking just at the natural gas picture, the technically recoverable reserves, as you can see, were around 290 trillion cubic feet back in 1967. That dropped down after some acquisition of those gases by 1994. And then after the discovery of these new technologies, the amount of technically recoverable reserves has just skyrocketed. And even this graphic is dated. And you can see the steepness of that curve. I don't know what the latest number is. In fact, it changes so rapidly anymore that it's I think it would be I don't know that anybody really knows what the number is at this point. It's just a tremendous amount of available resource that we now have. And there are shale resources also around the world. There's a whole lot of them in Canada, and South America, Africa, China, Europe, etc. And there's many parts of the world that have not even been studied at all. So there's a graphic, currently known global shale resources, and just the area in red is assessed, generally assessed, and then some yellow areas are assessed without a resource estimate, and the white areas are countries that are sort of within the scope of study by the Energy Institute Administration, and then all this gray area around the world is really outside of the scope of the study. So there's a tremendous growth in the amount of information that we have about this resource and the expected quantity of it around the world. And to give you a perspective on what a trillion cubic feet of gas means, a trillion cubic feet is enough to heat 15 million homes for a year, or generate 100 billion kilowatt hours of electricity, fuel 12 million natural gas vehicles for a year, and some of the more recent estimates that I've seen is that the recoverable resources we have in the U.S. is equating to about 120-year supply for the United States. And I would expect that number is actually going up from the information that I'm seeing. And as I mentioned before, there's lots of oil and natural gas liquids to be recovered as well. Some of you may have seen this Time magazine cover several months ago. It says, "This rock could power the world." It's an article about shale. And in fact, that's not an understatement, I don't believe. So I have a representation of supply and demand. And again, I'm kind of comparing natural gas and oil just so that you can get a feel for the importance of the natural gas aspect of this. In January, and I haven't updated the slide, but in January, on January 14th of this year, a barrel of oil was $93.56. A million BTU of gas was $3.33. And 1 barrel of oil equivalent is equal to 5.8 million BTU. So what that equates to is that a barrel of oil equivalent of natural gas costs about $16. So when you compare $16 for the same heat quantity, the same BTU, as a barrel of oil, what you see is a very substantial driver to a creation of more demand for the utilization of natural gas. And in fact, we are observing that taking place, is a much more growth in natural gas utilization. Now, I'm pulling up a rather complicated looking graphic. It's called Sources and Use of Primary Energy in the U.S. with natural gas highlighted. And on the left side of this graphic is you see the various supply sources that we have, and on the right side you see demand sources. So as you can see, the largest supply source we have is petroleum, and the smallest in this particular case is nuclear. But what I'd like for you to focus on is on the right side of this schematic, you see that 3% of the energy utilized for transportation comes from natural gas. and only 18% of the energy utilized for electric power comes from natural gas. And there's a really important reason for that, because for many, many years, natural gas was considered a very limited resource and a rather unreliable resource. It was subject to a lot of ups and downs in production, and we just didn't think we had that much in the United States. And in fact, in the 70s, there was the Fuel Use Act, in essence, even prevented the utilization of natural gas for large-scale power production in order to protect natural gas as a means of heating homes, et cetera, for residential use. Well, now that picture has changed tremendously. We have more natural gas than we know how to utilize. And in fact, it is a much better option from a carbon release standpoint. If you burn natural gas, you in essence create about half the CO2 that you get from burning coal. So from a standpoint of potential impact as a greenhouse gas source, natural gas is really favored in the power production arena. So what's happening today is most new power facilities that you see, and even quite a few shutdowns of coal facilities are taking place, and the shift is taking place towards natural gas. So you'll see that 18% number go up dramatically, and this is also having a very substantial effect on our release of carbon dioxide to the atmosphere. Much better numbers there. And we also will see and are seeing a conversion of transportation to natural gas, and typically large fleet vehicles where they can have a centralized fueling location like metro buses and delivery trucks, etc. Large-scale vehicles that can count on centralized fueling. So we're in the midst of a transition in both transportation and in electric power towards much more utilization of natural gas. Now, what you see now, I hope, is an article. It was in the Wall Street Journal on January 10th, and the article says the foreign policy uses of an energy bounty. And in essence, the point of the article, the viewpoint is, now that we have so much energy available to us for development in the U.S., and much of it in the form of natural gas, that, say, as recent as 2007, we thought we would be building, I think the number's around 10 LNG, liquefied natural gas import facilities in the United States. Well, the number is reversed now. In terms of those facilities are being planned for export of liquefied natural gas now because of our discovery of so much resource here. And this creates a very substantial geopolitical shift globally as well. It gives a lot more power to the United States and other countries. We don't have to rely on countries for our oil and natural gas so much that we may not, feel so comfortable with. Venezuela being a good example of that. Iran being a good example of that as well. Now we can be much more reliant on ourselves, and in fact we can provide this resource to others around the world, and it's become quite a significant geopolitical tool for the United States. Okay, so that's just a sort of a general viewpoint of the significance of this, of what has occurred in oil and gas development here recently. Now I want to talk a little bit about environmental concerns and get somewhat specific about water. So the environmental concerns for unconventional oil and gas development can be simply broken down into surface concerns and subsurface concerns. And the surface concerns include things like air emissions, surface water resources, potential impacts to surface water quality, land impacts from drilling and construction of water pits and chemical storage and erosion control, things of that nature. Infrastructure, lots of roads and compressors and pipelines and water treatment facilities and other surface disturbances. And very importantly, lots and lots of truck traffic and road damage. I was just driving in West Texas last week, and it's just frankly, it's dangerous driving down these country roads. There's so many very large trucks moving very large equipment, and a tremendous amount of it. And you see that kind of activity taking place in these areas of the country where this development is very concentrated. The subsurface risks and concerns that people have can, largely be broken into two. Protecting underground water resources being a very important one, and also some concerns about potentially triggering seismic events. There has been pretty substantiated research that injection of fluids in waste disposal wells, very deep waste disposal wells, can trigger small seismic events. Generally 2 or 3 Richter scale magnitude events. Not often, not regularly, and generally not at a level that is of high concern, but it's still a substantive topic to be aware of and to be observant of and react to as we need to as this development continues. If you're interested in that aspect, I would refer you to the U.S. Geological Society. They're in the midst of studying those matters pretty significantly. There's a Dr. William Lyeth, who I think has done a very thorough job of representing the research behind that, as well as some clarity on what the USGS's views as manageable and relatively low risk of seismic events. So I'd like to concentrate on water management and treatment at the moment. So hydraulic vac fracturing is really the most significant matter. It's a new aspect that is creating a great deal of interest in this oil and gas boom, if you will. So typically a well will require between 2 and 12 million gallons of water to be utilized per frac. It's a lot of water, but actually, relatively speaking, comparatively to other water uses such as agriculture, power, and mining, and municipalities, it's a very small water footprint. However, it's a new water footprint, and it has some people concerned about water quality, and then certainly in drought-stricken areas, there's not much room for a new need for water in some areas. So it can be a rather significant additional demand on water use. As I mentioned previously, there are some chemicals that are added to that water along with sand as a proppant. Those chemicals are very low concentrations. I think if you think of it like conditioning a swimming pool so that it behaves in the way that you want it to behave, that's what happens in the oil field too. There are corrosion inhibitors, there's oxygen scavengers, there's what they call friction reducers, anti-scale type additives that are provided to that water as it's pumped down in the ground under high pressure. And after they complete that fracture, then there is a recovery of some portion of that water that was used. In some formations around the country, a lot of that water is lost to the formation and it comes back to the well over a long period of time as what they call produced water. In other formations, quite a large percentage of that comes back very early in the process of getting that well ready for production, say in the first week or two. But typically 20 to 40% of that frac water comes back as what's called flowback water, which is the initial flowback, and then more of it comes back over time as what's called produced water. In essence, flowback and produced water are the same thing. It's just at different times in the life of the production of the well. So, shale development and water. This creates a really important organizational, management, political aspects as well to how an oil and gas company does their business. Water has always been a fairly significant aspect of oil and gas development, but in the past it's been primarily associated with having to handle formation water that comes up with the oil. And usually that was done in a fairly simple way of re-injecting it back to the formation in what's called an SWD, a saltwater disposal well. Well, now there's much greater degree of complexity to this whole matter of water management in the oil field. It's really important to effectively source that water, make sure there's enough available to progress your program. Transporting that water through pipelines or trucks in an area where the development activities are evolving greatly over a period of time can bring complexity. Storage of water is very important, and part of storage is preventing evaporation, particularly in arid areas. That's a really important aspect of it. That water that comes back out of the ground as flowback or produced water may need to be treated. In fact, more and more it's going to need to be treated. It also may need to be reused for a variety of reasons. It may be forced from a regulatory standpoint, and in some cases it's going to be necessary just in order to have enough water to progress your program. And then there's disposal of it. Once that water gets fouled by the formation to a certain degree, and if you're not spending the money to treat it to a quality to reuse it, then disposal is an option. And traditionally, that has been the oil field way, is to take produced water and dispose of it in very, very deep saltwater disposal wells, Class 2 injection wells, which are regulated under the Safe Drinking Water Act as Class 2 wells. And then, of course, there's a need to protect water, and that's both quality and quantity, and that relates to surface water and groundwater. And from an oil and gas development standpoint, and from a standpoint of those of us that are supporting the responsible development of this resource, the importance of planning it very, very effectively. All of these matters of water management and how they fit together with respect to the drilling plans and the life of a well field and the way that a water balance for that well field will change over time, et cetera. Those are all very complicated issues, and they translate to a tremendous cost for the operating companies. So what's occurring today is that water is one of the best opportunities for an oil and gas company to differentiate themselves from the competition. Those that can handle and manage their water most effectively and most economically will have a competitive advantage over those that do not. Not to mention the importance of protecting resources and public relations and other aspects of making investors happy, et cetera. So a great deal of emphasis and focus these days on the importance of water management in the industry. So from a standpoint of groundwater and surface water concerns, I think these can be broken into about roughly four categories. There are concerns about surface activities, potentially resulting in illicit discharges of waters that are polluted. There are some folks would suggest concern about, is it possible to contaminate a groundwater aquifer through the process of fracturing? And then as well as that, there is concern that if a well is not properly completed by the oil and gas operator, is it possible that a freshwater aquifer could be contaminated via that mechanism as well? And then finally, the issues of aquifer depletion. And I come back to arid areas because I think this is really where that's the most significant concern is there is no surface water. In certain areas where there's a tremendous resource, there is no available surface water for usage. So the water source is going to be groundwater. And the potential to deplete sources of groundwater is very real and very important. And we're seeing a lot of activity with respect to that in the arid regions of the country. Now, from my perspective, what I've done here is I've highlighted the two areas that I think are most significant amongst these four categories. And those are surface activities, the protection of surface waters, surface features, et cetera, and aquifer depletion. The reason that I point to those two as being most important from my view is that the process of fracturing, there really is very, very little opportunity to contaminate a groundwater aquifer from the process of fracturing in a well that is constructed to effectively acquired oil and natural gas. And there's a number of reasons for that. The primary one, there's the primary two reasons for that is the depth of the resource compared to the depth of groundwater aquifers is very, very different. The depth of the resource is often, 8,000, 10,000, 12,000 feet deep. Aquifer depths, usable aquifer depths rarely go below about 500 feet. So you have this tremendous depth, zone between freshwater and the zone of fracturing that is largely impractical, if not impossible, for fracture water to make its way against gravity, against density variance, etc., up into an aquifer zone. And so there really is no, there are no known cases of the process of fracturing actually resulting in a contaminated aquifer. Now, it's theoretically possible that it could happen if, for example, a formation was close in proximity to an aquifer, say a shallow formation. And in those cases, certainly that would need to be paid more close attention to. But in our cases here in the U.S., the depth difference is tremendous. In well completion, there is a very specific process of constructing a well that isolates those aquifers. And in essence, if there was a breach in that well in any way, under pressure from fracturing operations, that would be observed by the monitoring activities of fracturing, and it would have the extra protection of these double casings, etc. And I think what's important to also realize is that it's only during this discrete period where the fracturing is actually taking place, which is about a week in time for development of a well, where there would even be a possibility of there being a connection to an aquifer. But as I've said, I think the reality of the process and the technology and the geology is such that that is not being found to be a high risk. But these other areas are important, and we certainly need to continue to pay attention to the potential for contamination of surface waters and groundwaters as development continues. So I have a very simple graphic called Shale Oil and Gas Water Treatment and Disposal. And on the y-axis you have cost, and on the x-axis you have complexity. And so in the very simplest terms, low cost, low complexity, treatment for deep well injection. In essence, what they do is just remove any remaining oil on the surface of their collected produced water and then pump that water down into their deep well injection. The next is treatment for reuse and fracturing. And that is taking out any materials such as solids or oil and grease and maybe some conditioning for scale inhibition and things of this nature, biological control, etc., for reuse of produced water in fracturing. More complex, more costly, but most complex and most costly is taking produced water and treating it to a degree to where it could be usable, beneficially reused, or discharged to a surface water. And the reason for that is that when water is placed down into these formations, these deep formations, it comes into contact with very saline materials. And so it comes back out of the ground in a very salty form. And I have a graphic that is next here, and it's typical flowback water characteristics. And what you'll see, it's got two curves shown on it. This is a period over about 23 days of monitoring both volume and total dissolved solids concentration. And what you see with the red curve is that very early on, in the first 7 days of flowback, there was a lot of volume that was recovered. But that volume went way down after about 9 days, and then over a period of 23 days, very small quantity of produced water continuing to be recovered. On the other hand, total dissolved solids concentration goes up over time, and the reason that is because that water makes contact and stays in contact with the formation and picks up salt. So you can have relatively low salt fracturing water going down into the formation and coming back in the form of a highly saline produced water. And that is a very significant challenge when it comes to treatment of produced water, because the cost of removing total dissolved solids from water, reducing salt concentration in water, is very high. There's a few technologies to do it, but they're quite expensive, and that's a real challenge to the industry. So there are a number of major water challenges in the industry. Regulations are changing rapidly. The industry needs to be responsive to that. The agencies are stretched thin in determining which changes to make. Legislatures are grappling with it as well, and what laws to pass in order to react to this tremendous boom in activities using these new technologies. Well, using fracturing and horizontal wells. Water balance changes over a life of a field, so what you might try to design to deal with today in order to support a drilling operation is going to be different than what you might design 10 years down the road when there's possibly not a lot of drilling activity taking place anymore, but there is a continued recovery of produced water that's taking place. So water conditions and quantities will change over the life of the field. Those water quality variations are very significant geographically and even over time, as I just said, over the life of the field. There are very limited water availability issues in some arid locations. In other locations, there's plenty of water available. Let's take the Marcellus Formation, for example, up in Appalachia, Pennsylvania, West Virginia, New York State. It's really not a limitation on available water for fracturing. However, the geology up there is not conducive to effective development of disposal wells. There's just not a highly permeable, deep zone that would be available to build injection wells. So currently there's a tremendous amount of recycle taking place up there, and water that has to be disposed is trucked over to Ohio where there are some disposal wells. So there are different drivers with respect to water disposal as well. And then there are important decisions to be made about, if you're going to build treatment systems, should they be mobile, should they be centralized, where should they be placed, et cetera, et cetera. So again, a very complex matter with respect to water management. And when you get to treatment technologies, depending on what you're trying to accomplish with treatment, there are a lot of different technologies out there that can be utilized for various aspects of your treatment intent. And what you see here is just a tabular representation of a number of different kinds of technologies and what those technologies are applicable to addressing from a water quality standpoint. And the significant aspect of what I'm showing here is that proper decision-making process with respect to how to treat water in the oil field does require quite substantial engineering analysis. There are a lot of vendors that are trying to solve some of these issues with single technologies or black box technologies, proprietary technologies. But the industry, I think, is beginning to really realize that this is a very substantial engineering challenge to properly address water treatment type matters in the field. So from a treatment summary standpoint, deep well disposal is clearly the most economical, except where it's unavailable, as I mentioned up in the Marcellus region, Pennsylvania. Recycle and reuse approaches are very desirable. The industry recognizes this. In fact, in some areas they're really pushing it hard because they realize they're going to run out of water if they don't figure this out quickly. And the regulatory authorities are also pressing for this. In some places there will be requirements for a certain percentage of water use to be from recycled water for reuse. We'll see that soon, I think, in some of the arid regions of the U.S. The selection of mobile or fixed facilities is a real key decision. Total dissolved solids, TDS, removal technologies are very expensive and complex, and they require very comprehensive evaluation and design. And there are many applicable treatment technology combinations that require, from my perspective, that really should get good independent engineering evaluation and design. And I tell our clients this, and I think many are beginning to realize this: beware of black boxes as solutions to their issues. So now I'm going to try to just give you some food for thought in terms of what I think are some opportunities for research and development with respect to water. Okay. Number one, the industry would very much like to see methods for reducing the need for water in hydraulic fracturing. And they're putting a tremendous amount of money into that research. And a great deal of money is also being spent in that research by the service firms, the Halliburtons, the Baker Hugheses of the world, the Schlumbergers of the world that provide large-scale service to the oil and gas industry. So I don't know that from Auburn standpoint or other universities, that would be an area of primary focus, because I think there's just so much research taking place there by the people that really understand it, the folks in the field that know about fracturing technology. Maybe not much opportunity there. A lot's already taken place. The second item is water reuse treatment optimization. I do think that this is a very dynamic situation taking place. It's a battle of the black boxes. And I think there could be some valuable focus on trying to make sense of all of this and to really bring some good guidance to the industry on when certain technologies are most applicable and zero in on the best recycled technologies. So that's an area where I think some university-oriented research would potentially bring some value. Next would be removal of dissolved solids from water. Currently, there's basically three technologies that can be applied for this. There's reverse osmosis. I mean, there's others, ion exchange to a small degree, but that's in low concentration. In relatively high concentration TDS waters, reverse osmosis can be useful up to a concentration of feed water concentration of, say, around 40,000 milligrams per liter. Okay. Anything above that, and you really begin to not, it's a point of diminishing returns using reverse osmosis. And that's for various reasons beyond the scope of this discussion. Next, evaporation technology can treat water up to a maximum of, we'll say, around 100,000 milligrams per liter. And then beyond that, you're forced into crystallization technology. And those last two, evaporation and crystallization technologies, are thermal technologies. And they're very expensive because they require a tremendous amount of energy. So there is some development taking place in new attempts to develop technologies for dissolved solids removal using things like membrane distillation. There's some firms that are studying forward osmosis, not reverse osmosis, forward osmosis. So there's probably some substantial research opportunity for academia to engage in that arena and to find some solutions for removal of dissolved solids from waters. And then in terms of the thermal technologies, evaporation and crystallization technologies, ways of improving the energy usage, such as co-locating these next to compressor stations and picking up waste heat from the compressor stations and utilizing that waste heat for driving some of these technologies is another area that's potentially valuable. And then finally, study and mapping of brackish and saltwater aquifers in arid regions. Now, I think this is really very, very significant in arid regions. Most knowledge that we have about groundwater resources has been focused over the years. The efforts to understand groundwater resources has primarily been focused on high-quality waters, potable water, drinking water, quality waters. And once you get to the brackish and saltwater arenas, not so much focus. So our understanding of the resource and locations and producibility of groundwater zones that carry brackish water and salt water is relatively limited. It's another area that I think is likely to be of high importance for gaining more understanding because more and more brackish water and salt water is being utilized in the fracking process itself. Originally, when fracturing was first applied, and even up until fairly recently, there was kind of a demand for very high quality water to be utilized in that fracking fluid. And the fracturing companies have learned that they can get by with using saltier and saltier waters. And so now we are actually able to fracture with water quality that maybe we didn't imagine we could utilize in the recent past. So in a nutshell, I would say those are the opportunities that strike me as areas that maybe some of you on this call could think about spending some time on. And that concludes my presentation. So I'm certainly willing to try to answer some questions.
Mr. Nolan, this is Vicki. I have a question from our attendee, Shuchi Sharma, and he says, in an industry best practices type scenario, would you have a figure on what is the cost component of water management in a fracking operation?
Well, I can give you some rough numbers here. Typically, the purchase of fresh water in the area that I'm familiar with is about 50 cents a barrel. Purchase of groundwater, freshwater, groundwater for use in fracturing. About 50 cents a barrel. That's a 42-gallon barrel. And by the way, the oil and gas industry speaks in barrels. They don't speak in gallons. I spoke in gallons today because I think many of you might recognize those figures better. But so about 50 cents a barrel. So 50 cents per 42 gallons of fresh water. Depending on how far that fresh water needs to be transported to a location for fracturing, that can add another maybe $1 a barrel commonly. Then you have the cost of disposal. Now, if a company owns a disposal well, which is the case in a lot of locations, you're again at around 50 cents a barrel for disposal, and that number can go up to maybe $3 a barrel for disposal. So can be fairly substantial. And then, of course, you've got transport of that water to those disposal locations. So add another $1 per barrel. So you've got, $2, $3, $4 a barrel typically, and in some cases a whole lot more than that. And when you start to bring treatment technologies into the equation, that of course adds to it even more. And that varies tremendously. To simply remove solids or oil and grease from the water, maybe can be measured in a few cents per barrel on a large scale. But when you start to thermally evaporate water, et cetera, you get into the multiple dollars per barrel. So the answer to the question is variable depending on the situation and the location, but those are some numbers that maybe would be useful to the person that asked the question.
All right, and we have another question from John Bradford saying, for many years we have had an inequity in the rates between our use of oil and Mother Nature's ability to make it. No amount of inventory can sustain a rate imbalance for very long. Can you give us an idea of our rate of use of natural gas versus Mother Nature's ability to produce it? Yes, we have found a previously unrealized inventory, but with a rate problem, are we just setting our future generations up for a fall from an economic cliff? Does this economic future come into the planning models of which you speak?
It's really excellent. It's an excellent question. And the answer is yes. We're going to produce natural production of natural gas and oil happens over millennia. So we are in the process of mining the available resource, and it will not be produced at a rate that can possibly keep up with, even close to keep up with the rate that we are mining that resource from the earth. So in the end, we will become limited by the amount of this resource that is available to us to support society's need for energy. And we will have to replace that with other technologies. And so there needs to be a continuation of development of renewable technologies. There is a lot of effort taking place there. I personally am interested in the ITER project, the International Thermonuclear Experimental Reactor Project. It's a nuclear fusion project. It's a multi-country effort for development of the first massive scale nuclear fusion demonstration project that is currently located in France. The schedule for that getting to a point where it is supposed to produce energy through fusion is, as I understand it, around 2030, with an expected additional 30 years after that for development of the first project that could actually deliver energy from that technology to the users. And maybe you're talking about a 100-year period of true development. So we will have to replace ultimately fossil fuels as our primary energy source. But that could be 100, 200 years from now, and I think the amount of available energy that we are seeing today indicates that we've got time to address that issue, but we shouldn't slow down in the focus on it.
Okay, Hunter, we're out of time. I want to go ahead and do a few concluding remarks, give Stan Graves a chance to talk, and then anybody else who has questions and want to stay online, as long as Hunter's available, certainly we can stay as long as we need to. Stan, are you available to speak at this time? Okay, apparently we haven't got Stan connected yet. I do want to thank Hunter for the excellent presentation today. Really appreciate him stepping in. Sam Fowler is the Auburn researcher who leads in this area, so if you have questions and you want to email Hunter, it'd be good to copy Sam on those questions as well. We'll have a link to this session was recorded, so we will have a link to it for people who could not participate at this time, can go back and look at it in the future. We do want to remind people that civil and environmental engineering has several other people doing water quality related research. In fact, if you look at the latest issue of Auburn Speaks, it's Auburn Speaks on Water, and it covers a number of those programs where the research is ongoing at Auburn today. Our next sessions, reminder again, June the 12th, we'll have Dr. Virginia Davis and some other researchers out of the Composites and Materials Department talking about nanotechnology, bio-nano, and polymer research. And then on July the 10th, Dr. Charles Ellis and Dr. Mike Hamilton will be talking about microelectronic packaging and nanotechnology. We would like your feedback. This is our first webinar. We will have several of these in the future, so anything we can do different, anything to improve them, please send us email to Vicki and myself and let us know. So at this time, we'll open it back up. Vicki, if you have any more questions, or if people online have questions, and the people who need to go can, people who can hang on and talk with Hunter are welcome to stay as long as he's available. Thank you for participation today.
Yes, I don't have any more questions sent to me, but they can come from the floor as well. All right.
Hunter, this is Larry Filmer in Auburn. I just wanted to add my thanks to you for your effort, and Vicki and Rodney and Barbara who are on the line. Just thanks to all of you for getting this set up. I thought it went extremely well for the first time, and Mr. Nolan, your presentation was superb. We really appreciate your effort on this.
Oh, well, thank you for that. It was a pleasure.
All right. Thanks, everybody. Have a great day.
Bye-bye.